Okay, so this is a problem that I kind of keep coming back to from time to time, and so the results I will be. So the first thing is, I think the title that I had sent to Odunavu was this. Odunavu wisely added an on to it, I think, in the no, doesn't matter. What I was going to say was that that was kind of wise, because an on, of course, suggests that it's something where I'm not going to say something definitive. It's a kind of some thoughts and all that, and that is what it will be. As you will see, it will be kind of a combination of some stuff that was done some time back and some stuff that I'm doing now or thinking about now, and yeah. So since I was not sure about how much people in the audience follow this field of QGP, I added quite a few kind of elementary slides. So at large temperatures, we know that strongly interacting matter exists in a deconfined chiral symmetric state that I guess everybody knows. It's called quark-gluonplasma, or QGP in short. And what we also know is that at large temperature but no net baryon density, this transition is a smooth crossover. And here's a slide that kind of illustrates that from this reference. So this is the susceptibility of the chiral condensate. So chiral condensate acts as the order parameter for this movement from the confined state to the from the chiral symmetry broken state to the chiral symmetric state. And as you know, the susceptibility of the order parameter is expected to diverge. So if you take a finite volume system and keep increasing the volume, then the susceptibility should be, peak should be steeper and steeper. And what you see here is as the volume changes, okay. So what is given here is kind of number of data points in time direction in the inverse temperature direction, and this is the number of data points in each of the space directions. As you see, this increases. There is a susceptibility peak, but its shape doesn't change. So it's not a transition, but a crossover. And this is.
This is for 3 quarks, of course, but also the masses are put in and so on. Is that
yeah, so the
realistic value?
The mass, okay, it's pretty close to the real quark mass. So now we also have studies which are at the real quark mass or even lower than the real quark mass. But this was kind of a nice plot, and it came in Nature, so I thought I should show this. This was, if I remember correctly, something that had a pion at something like 160 MeV. So slightly heavier than normal pion, but now you also have simulations at real quark mass. And the strange mass is correct. So it's 2 + 1 flavor, and the light quarks are slightly heavier than real U and D.
And sorry, just to complete, the order parameter is what exactly? Q bar Q summed over flavors?
That Q bar Q summed over flavors. So what we take is so something like, so the light quarks, and you take something like U bar D, let's say. Okay. So it's the off diagonal thing. Okay. So the thing is that so I should have written U bar D minus D bar U or something, the one corresponding to sigma 3. But in these simulations, actually U and D are the same. So when you are doing this, you are essentially, the reason why it's U bar D and not U bar U is because you do not allow the U and D to, these 2 quarks in the chi to contract between themselves. Okay. So.
And suppose we worked with a model in which all quarks had 0 mass, so chiral symmetry was really asymmetric.
Right.
Logically, you could have had a deconfinement transition and a chiral symmetry restoration transition as separate transitions, right? You seem to be sort of more or less identifying them here.
What's the order parameter for deconfining the fundamental quarks?
You're right. Fundamental quarks is only one. I'm sorry. Thank you.
Okay. Okay, I mean, so in principle, of course, you can look at the Polyakov loop. It's not an order parameter, but nor is this object when there is a quark mass. Okay. So what happens? Okay.
In large NQCD, it could have happened, right? Large NQCD, there's a sharp order parameter there.
In large NQCD, there is a sharp order parameter.
Free energy divided by n squared.
Right. Okay. So I think the answer is that we don't know. I know what happens here. So what happens is if you try to track this, in fact, that's in my next slide, and this is essentially just an illustration of this.
Essentially irrelevant, so you only have a deconfined.
Yeah, you could, okay.
Technically, this one is only a chiral phase transition, as Saumen said, to the extent that you are approaching it as an approximation from the m close to 0 m.
Right.
And there is no order parameter for deconfinement at non-zero m.
Right. But in large NQCD, it's true that the quarks are essentially irrelevant, but if you study the dynamics of the quarks for that, they're not irrelevant.
Yeah, but thermodynamics they don't contribute.
Not in thermodynamics. But
And so the phase transition is governed only by gluons.
okay, for the free energy of leading order in n squared.
Yeah.
But you could still ask whether there is an expectation value of psi bar psi or not, whether that's 0 or not. And that might be
It then becomes a matter of unity.
that's right. There are actually.
In the old days, this was claimed to be the case, that both psi bar psi and L have a first order phase transition.
Separate.
At the same place.
Separate.
And if you want separate, then you have to have not fundamental quarks but adjoint quarks.
Yeah.
What is L? The free energy over n square.
Sorry?
L, you said.
L is the Polyakov.
Okay.
Just to say, within holographic theories, there's a theorem
Yeah.
which gives the order of these phase transitions.
Yeah. In fact, deconfinement happens first.
Yeah, then the
balance into restoration.
No, in large N also, there is a...
So is that something that uses?
that is first order. In holographic theories, there's a theorem that says that these things can be separated, but if they're separated, there's a particular order. You can't have one rather.
No, there has been already an argument based on what I would call as some kind of a Banks-Kasher relation kind of a thing from in the Pisarsky, which says that deconfinement has to happen first.
Okay.
Right. Yeah. Okay. So okay. So let me tell you what happens in this case, and then forget about large n. What I think will happen.
I'm very sorry, just for my own
Right.
remedial, but in large n, the free energy over n square, if you use that order parameter and you use the Polyakov loop, are they the same? Is it obviously the same?
Well, if they are both associated with deconfinement, so one would normally expect them
Yeah.
to
Sounds
be,
very reasonable.
yeah.
I'm just asking,
Yeah.
is that a...
Okay.
But basically, if you think of it, effective action of the Polyakov loop, the gluons contribute n square, the quarks contribute n, so the leading order is basically
Right.
so you can forget it. And that's-
Okay. Well, of course, I mean,
Eliminating the quarks anyway.
yeah. So the
Eliminating the quarks.
free energy, of course, has more than just the
Yeah.
electric gluons. So,
That's what I'm saying.
yeah.
Well, it's conceptually
I would say that your statement on order n squared is correct, but just by dividing by order n squared, you won't get 1, in the sense that there are other constants that you will have to worry about. But if you don't worry about constants, it's the same.
okay. Now I was thinking of the constants. But
So if you worry about the constants, it's not the same.
Well, free energy by n square and Polyakov loop in every transition I'm seeing is the same order.
No, true, but the factors which will multiply the free energy will not cancel by having divided by n squared. So I don't remember the factor, but it might be some pi square, 8 pi square.
Correct. But
And in that sense,
No, I think what Sandeep is saying, I mean, in the free energy, of course, you have electric and other kinds of gluons. In polyatomic loop, you only have electric gluons. But yeah, in large N, you expect them to have the transition at the same point.
When the gluons are basically deconfined.
Exactly, yeah.
That's when the
So in large N, you expect them
Sure, I
to.
agree. I just wanted to know whether quantitatively it would be exactly at the same
Same point, yes.
It will happen at the same temperature, but the rise will be different.
Yeah. Large N pure gauge theory, this transition is well studied, of course. I mean, we studied it, and there, of course, you see this a transition that gets more and more strong first order as you increase N, and there, of course, the two transitions happen at the same place. Okay. So what happens here, however, is that because it is a crossover, the transition temperature depends on what you choose to monitor the transition. I mean, here in general there is no order parameter, so you can track it by chiral condensate, you can track it by Polyakov loop, and you can track it by rise of the energy density, for example, and they give transition temperature which is slightly different. So something like in between the range of let's say 150 to 175 MeV, something like that. Okay. Now, so if I kind of draw some kind of a diagram against quark mass to show where I get crossovers and what, I mean, I would expect that there will be some small value beyond which of quark masses beyond which you get a first order transition, because the quark going to zero mass limit, you are expected to get a first order transition.
And that you know from whatever universality class.
That's right. Yeah, so the quark mass going to zero, you know from the universality class, and then you expect, yeah, so it to remain first order.
Can you give us that argument just briefly?
So essentially the argument is that the U1 symmetry doesn't get restored at the transition, and that adds something like a phi cube term to. So if you are writing an effective Ginzburg-Landau Lagrangian for the chiral condensate, then the term coming from the U1 symmetry breaking, because it's for two flavors it's quark to the power 6, right? No.
Two flavors is O4, right?
Yeah. Two flavors it's O4, and that is second order. That's right. So.
And what is the argument roughly?
For
Let's say this O4, just that there exists a second order transition with this symmetry, that there exists a conformity theory with symmetry.
Yeah. O4, there is what is the O4 class?
But this is just a sigma model?
That's right.
O4
Yes.
sigma model?
Yes.
It's just like
Yeah. So essentially the argument is just that there is this thing. Okay. So.
Wilson Fisher fixed point. An O4 Wilson Fisher fixed point.
That's right. Yes. Yeah. And
For the SU3 plus SU3 case,
that the argument is that there is no conformity theory with this concept. Is that it?
You could write cubic terms like determinants, because it's T, so T plus T would make a determinant. So then you can have cubic terms, and therefore you can have first order transition, depending on the sign.
No.
Know that it's not a second. Is there an argument that there cannot be a second order transition when there are three masses? Sorry, just.
no. Is there an argument that there cannot be a second order transition when there is
Three massless quarks. It sounded to me like the first argument was that it could have been first or second with two massless quarks, right?
with two massless quarks?
it's always that it could
have been.
right? I mean,
Yeah.
O4, I think, universality.
No. But the universality argument, of course, sets in when you have a second order transition. So based on universality, how do you say it's second order? That's what he is asking. And so again, some kind of the renormalization group analysis that Pisarsky and Wilczek did, I think what they showed is that if you now put in for three flavors, if you put in the determinant term, if the U1 symmetry is restored at the transition, then you are expected to get a second order.
Is relevant, you're saying. Yeah. Am I understanding right that you're saying that the only known conformity much larger symmetry.
Only known?
Non-conformal theory has a much larger symmetry. Or not? Sorry, please, you say it.
Well, so of course you could write down so let's say I don't have the determinant term. Then I think it will give you a second order transition.
It's possible to write like inspect and
I think the argument is that generically when you write down, there is no reason why you can solve it that way.
I think that's
Right. So you want so let's say you are writing Ginsburg-Landau Hamiltonian for chiral condensate, then you need to have something like a sigma cube, okay, in order for it to be second order, first order, okay, and that comes when you have the determinant term. So that's the argument that
Could I
is
word it in this language? That there exists a conformal field theory with this symmetry, but it has two relevant operators rather than one. Is that what you're saying?
There exists a
conformal field
No, the statement is not whether there exists a theory or not. Even if it exists, in order for it to be relevant to this symmetry, you will have to come up with an argument. Why is it relevant to SU3 cos SU3? Because determinant in general is allowed.
Right. Isn't that the statement that there are two relevant operators rather than one? Because you're doing one tuning.
okay.
So if you had just one relevant operator, you would expect to hit this point. But if you have two relevant operators, you would expect to miss it.
Uh-huh.
Yeah, but what Rajiv is saying is that you don't need a fixed point for that, just as long as you have a five, you have this jump. Because I don't know, I guess the fixed point would be the Wilson-Fisher analog with,
So it is also true that in general these fixed points are not known, but there is no theorem that it is.
Does not exist. I see.
Yeah.
Firstly, we don't know if the fixed point exists. Secondly, if it did, we
Yeah.
expect it to have two relevant.
Yeah.
So it's irrelevant. Okay.
In fact, I think there is no clear indication from lattice that you indeed have this first order region. All attempts to actually go down in mass to get a first order region just keeps pushing this boundary to lower and lower quark mass. Okay.
And what about zero quark mass? You can't do that on the
You cannot do that on the lattice. But that's what I said. I mean, all attempts to push it down essentially just gets
So
this
is that
line.
real theorem that there's a first order phase transition as an expectation?
I don't think there is a real thing. I mean, yeah,
So maybe wrong. That's an interesting problem.
could be wrong. Yeah.
That's interesting.
Right.
No, I think the fact that it is wrong is not an interesting thing as much as coming up with something which will kill the determinant for some natural reasons.
But
Right.
suppose it was wrong, you have an identification of then there's a second order transition presumably.
Right.
And is there a conjecture for what that second order fixed point is?
No.
So that's the interesting question, right? You identify the second
That
order
is
element.
That is true. But this is true in general Z free space.
Okay.
Yeah. Right. So anyway, so like I said, in the crossover region you have a spread, right? Once you enter the first order region, if there is one, then I would expect the chiral condensate, of course, to show a jump. And if L doesn't show a jump there, then L is not going to show a jump anywhere else, I guess. So, right? I mean, it's not an order parameter. Why should it all of a sudden show a jump somewhere else? Yeah. Okay. So, anyway, so like I said, the transition temperature is somewhere in the range 150 to 170 maybe, depending on which object you use to track it. So that is above 15 billion kelvins, and I thought I should add something which is relevant to chemistry. So I added this part, but don't ask me anything about that.
way after the time.
Right.
I don't know whether the time is quantum at that time. Space maybe. I don't know.
Right. And okay, so there is theoretical expectation that the transition may turn first order at large baryon chemical potential. So typically we draw a phase diagram something like this, where you at large net baryon density you have a first order transition, and then it ends somewhere in a critical point, so that you don't have. So this is now for physical quark masses. What we really know is this part, and yes, those of you who have been here for a while know that you cannot actually, for various reasons, actually do lattice calculations at finite mu b. But Rajiv and Shaurendu have made very well known and great attempts to kind of make a prediction for the location of the critical point if it is there. So, and the most recent estimate of this is this recent paper which says that mu c will be, so if this value is Td, then mu c Tc is about this kind of value. So, it is almost flat in temperature direction, and this value is about 300 or so.
And what is the
maybe
universal, what is the expected universal?
Z2.
Z2. What is the Z2?
The Ising universality, because there is no.
But what is the Z2 in the physical problem?
What is the Z2 in the physical problem? Yeah, that's a good question actually. Basically related to the
exchange of the two.
And the fact that you really, the strange quark is essentially given.
That's right, yeah.
Oh, so you're saying that of the proximal SO4 symmetry, only a Z2 is preserved.
And sorry, just to, since we are getting an education here, when you say it's deconfined, I understand the physical expectation that if you have so many fermions very
right.
mu, the Fermi surface itself is at very large mu compared to the strong coupling scale, you expect the system to deconfine.
Right.
But more precisely, when you say it's deconfined, is there an order parameter? Is it the Polyakov? What is the, when you say to the right, it's deconfined?
Yeah, so here in this diagram, when I say deconfined, I kind of mean that you are tracking it through the Polyakov loop.
Through the Polyakov loop,
yeah.
Okay.
Right. Okay. And how many more of this education? Okay, not too many. Okay. So you have more than the first 15 microseconds actually to study this quark-gluon plasma. So in lab experiments, one creates this phase. The way it is done is you take two very heavy nuclei and collide them. The idea is that collide them at high energies, and the idea is that, of course, at very high energies, most of the original projectile particles just pass through, but the interactions between them as they pass through, mediated by gluons, create a large region of gluon scatterings and rescatterings, and if it then stays for long enough for it to thermalize, then you will expect to get something like a quark-gluon plasma phase, because there's a lot of energy, it gets thermalized, so the temperature is high, and this is what one tries to study in these experiments. So the major player in this was, or I should say, is REEC. It has been running, giving results from 2001, and very interesting results. It was colliding gold on gold at 200 GeV per nucleon of gold. Gold has about 200 nuclei, 200 nucleons in the nuclei, and now it is actually, it gave very interesting results at this high energy regime, which was more an attempt to track that near the mu is equal to 0 axis, and now it is actually trying to go down in beam energy to study what happens, in here essentially, because as you go to low energy, the original projectile particles do not completely pass through, so you have a neat baryon density, and then the plasma that you create, if you create a plasma, then that will be a baryon rich plasma. Okay. Of course, LHC is also in the game. It's lead on lead at 2.8 TeV per nucleon, and then first at 2.8 TeV and then at 5.5 TeV, but most of the results we have till date are the 2.8 TeV run results. Okay. Right, there is
one order of magnitude. I'm sorry, lead is how many, like about
208.
Nuclear.
208 new.
So I thought LHC didn't go that high up in Because these are heavy. Okay,
Yeah, yeah. I mean, so essentially,
No, LHC did go in up to the level that he has said. You have 7 TeV on 7 TeV.
7 TeV on
6.5 TeV on 6.5 TeV.
Right, but he said per nucleon. So
yeah, but see,
half of that is that.
yeah.
Yeah,
See,
so
essentially
the lead having so many, the amount of energy you gain also depends.
Yeah, lead has lots of protons, right? And you are giving the energy through electric field. So
You should say protons and neutrons are the same.
Yeah.
So therefore factor of 2 eV by m.
yeah.
So whatever is the energy divide that will
So 14 TeV roughly comes to something like 5.5, 82 by 208 into 14. I guess it's a little less than that, but roughly in that region. Yeah, right. And then one estimates what's the initial temperature that was of the produced medium in these two collisions. I took these numbers from Rajiv's Valerao's DTP colloquium some time back. So in the LHC 2.8 TeV runs, the initial temperature was estimated to be about 470 MeV, which is way above the transition temperature that I showed before, which was like 170 MeV. And in REEC it was more like 360 MeV. Okay, and then what happens is that you create this medium, but of course it's very energetic.
This is an estimate for what?
For the initial temperature. So the way it comes is that, yeah, right. So well, or at least locally thermal. So you try to feed this with a hydrodynamic model, and then you see from what time do you need to start your hydrodynamics simulation and what temperature does that give. Okay, and yeah, so these are the estimates he quoted, and then of course it stays for some time, and eventually when the temperature, because the system is expanding, at some point of time it cools down sufficiently, and then it hadronizes, and then eventually it just becomes non-interacting hadrons. That time was estimated to be about 8 Fermi. So the total lifetime of this plasma was estimated to be about 8 Fermi in REEC and about 10 Fermi in LHC. Again, these numbers I took from Rajiv's colloquium. All of these essentially came from hydrodynamic fits. Okay.
So as it expands, what part of the phase diagram does it go through? Does this fireball go through?
Yeah. So it will go through something like. So let me see. So you will have. So the temperature comes down, of course, and so the mu here is already very low. In fact, for LHC, the mu is something like 27 MeV or something. But you make something like an estimate of an constant entropy kind of expansion, and that essentially gives, if the mu was slightly larger, then it comes down like this, somewhat like this. So you come down both in mu and in temperature.
But it doesn't come through the first order.
No. It's in the opposite way, in fact.
And when you go to very low energies, it still doesn't come through the first order.
So that's what is the aim of these experiments.
Yeah.
Okay. So like I said, as you go to lower and lower energy, you are expecting that you will start at larger and larger mu, and the question is, do you at some point of time have a trajectory, the isentropic trajectory, the constant entropy trajectory goes like this, and what they're really interested in is, of course, because you always want to get to the critical point, so they want to see whether you get a trajectory which comes sufficiently close to the critical point and stuff like that. Okay, so both of these will have interesting signatures. I think people are not very clear in their mind what those signatures would be, because the order parameter that connects to the critical point is, to the criticality is not very clear. Okay, so what is the critical field is not very clear, but yeah, if you.
But even going through the first order line will have some quite clear signatures.
Sure, yeah.
It's super cool bubbles, for instance. In the sense that you've got the fireball.
Yeah.
It will typically cool down to lower than the phase transition temperature.
That's right. It has to cool down to lower than the, yeah.
And then suddenly boom.
Okay. Yeah, right. That will require not only first order, but presumably somewhere here. So strong first order. Right. And But of course, the question is then you need to translate all that to an experimental signature.
Of course.
Yeah, and I think I'm familiar with the discussion more related to the critical point because people will already be happy if they can come here.
Right.
And I think that is one of the burning questions. What exactly will tell you that there is a critical point? Okay.
Just if you
I in fact recently gave a journal club on where I touched on these. But yeah.
No, I'm sorry.
Yeah.
If you just looked at the chiral condensate photoparameter you were using, that is not expected to have a sort of big.
No, because this Z2 symmetry is not. So the chiral condensate is not the critical field.
Yeah.
Whether it couples enough to the critical field to actually show some critical singularity, that's a different
We could devise
question.
something which is odd under Z2.
And also the other thing is that chiral condensate is not something that you can very easily see in the experiments. Okay.
That's right. I was just trying to
Right.
ask whether you could devise something that was odd under Z2 made out of the bilinears in quarks.
That's right. Yeah.
And
Right.
you expect that has some kind of a large fluctuation.
Right.
Suppose you make that assumption, would that translate to some interesting experimental signature?
That's right. So the signatures that people mostly look for are something like fluctuation of protons, because you expect the protons to couple to this critical field. That's what was the journal club was about actually. But anyway, yeah, right. But then, yeah.
One
Right.
probably should. I'm sorry.
Yes, no.
Okay. Could it be that you could have metastable ball of this fireball just sitting there for a while? You know, if you go below the phase transition temperature,
Right.
the pressure goes the other way.
Mm-hmm.
So you can imagine a situation where the surface tension balances the pressure, and it just sits there. Sort of oscillates, sits there for a while,
Mm-hmm.
radiating out stuff. So almost like a stable particle for a while. Could that happen? I'll ask you.
Why do you think that will happen?
It's a possibility, isn't it? Is it not? I mean, depending on how there's the tunneling probability, of course.
Uh-huh.
Suppose you've got a metastable region, it's always radiating out stuff because of tunneling.
Right. So you are thinking that as I cross this first order transition, whether I get metastable?
Let me say precisely. I think in the large N theory,
Uh-huh.
you would be able to find solutions
Uh-huh.
of balls
Yeah.
that just sit there and are stable for times of order n squared.
Uh-huh.
And I was wondering whether these might actually show
So
up.
this will be a ball of Polyakov loop of a different sign. Huh?
Ball of plasma.
Right. So the Polyakov loop is non-zero inside and
Outside is zero.
yeah.
So, I mean, just to understand, one thing is that if it's strongly first order, then you can get trapped in the false vacuum and then you have it.
Right, right.
You
I
create
think-
a bubble of the true
Right,
vacuum.
right.
But this is the opposite in a sense, right? Here you have a bubble of the deconfined phase, the plasma,
Yeah.
in a surrounding medium which has become now.
Yeah, let me say, I'm sorry.
Yeah. So he's saying I cross these and I get a bubble of deconfined plasma still sitting in
Yeah,
there.
let me say it in the large N theory.
Yeah.
In the large N theory, the phase transition happens when the two free energies are equal.
Right,
However, the free energy of the vacuum is almost zero because one is order 1, so let's call that 0.
right.
So the phase transition happens where the free energy of the bulk stuff is 0,
Uh-huh.
n squared times 0. But free energy is same as pressure.
Yeah.
So it happens when the pressure of the bulk stuff goes to 0, roughly speaking.
Mm-hmm.
Okay? So for this, in the confined phase, pressure, higher temperature, the pressure is positive, so the fireball keeps expanding.
Right.
But since it's going to 0 at this phase transition point, you can imagine a situation where it just sits there.
Yeah. So of course, because of confinement, there is a pressure in the confined phase also, right?
It's order 1.
It's order 1, yeah. Yeah.
So it's negligible compared. In large N theory, this is a precise.
But the transition is happening when the two are equal, right?
The two are equal.
Yeah.
But so the relevant question for the deconfined phase is n squared times a function.
Right.
So in that function,
Yeah.
the difference is roughly order 1 by n squared. The pressure of that function is roughly order 1 by n squared. It's very small.
Okay.
So that can be balanced by surface tension.
Right. Yeah.
And you
Okay.
could, in the large N theory, at least in some examples, these solutions exist.
Right.
These
Yeah.
things exist as stable things.
Uh-huh.
And I was wondering whether you might actually see this going to the detector.
Yeah.
So can I just ask you, in the large N theory, is
Yeah.
the tunneling to
to the power. No, it's actually it's Hawking radiation as well. So it's a one by
I know what I mean. But I mean, in real world, if you have this ball of plasma below the below the transition, since it's the false phase, wouldn't you just create bubbles in the true phase also? That's a competing thing, right?
That's a competing thing. So that thing would have an e to the power minus n square.
In large n.
In large n. So the question is that e to the power minus n square?
Correct, right. That's
You
what
know, exactly. Is the n equals 3 large enough for you? I mean, is it long enough to keep it alive till it reaches the detector?
You also have to remember the volume matters. These volumes are pretty small.
I see, yeah, that's true.
That is true. I mean, typical correlation length in the first order regime you would expect to be of order 1 Fermi. So that's the kind of bubble you're probably looking at. Yeah. Right. Okay. Okay. So now, why is it interesting to look at heavy quarks in all of this? Well, the thing is that, okay, first, what are heavy quarks? That everybody knows, right? I mean, essentially the mass is much larger than lambda QCD. So bottom, charm, top is not that interesting because it decays so fast that you don't see it. Okay. So the thing is, there are two things. First, typically you would expect, I'll soon say that that's not probably completely true about charm, but typically you would expect that the typical temperatures, initial temperatures that I quoted, they're not that much larger than lambda QCD. So all the charm or bottom quarks will be generated primitively. So they will not be generated as a thermal gluon going to a ccBar pair, okay, because the masses are too heavy. So whatever heavy quarks you are seeing, that essentially gets created very early in the collision and then essentially leads through the plasma. So it sees the whole history, okay. And so for example, since they are created in these early hard collisions, typically they may have a momentum which is much larger than the typical thermal momentum. So you can study the interaction of the plasma with particles by seeing how these energy goes away, how much the heavy quark is thermalized and questions like that, okay. And then of course theoretically you can use the fact that for example in bound states they are approximately non-relativistic to do various simplifications. So in some sense they work as a probe of the evolving medium. And so the other thing is that in fact the first people to stress the importance of heavy quarks in studying this plasma were Matsui and Zatz, who said, well, I create this QQ-bar pair early in the collision, but then if it goes through a deconfined medium, there's no reason for them to combine into a bound state. And since their density is not that large, if they don't bind initially, they are not going to bind. So you are going to see a strong suppression of bound states if you create a quark-gluon plasma. So they actually suggested these as some kind of an indicator that you have formed a bound state. And then there were some more detailed, but in retrospect, kind of naive estimates of at what temperature the different quarkonia states will decay, and therefore the suggestion was to use these heavy quarkonia states, which are the heavy quark bound states, as some kind of a thermometer for the plasma. Okay.
Sorry,
yeah.
Can I just ask it? Because what about a heavy light bound state? That is to say, suppose you formed a meson, charm meson or something.
Right.
Now you go through a deconfined phase. Again, that would just get ripped apart.
Right.
But
See,
that be something that.
so for example,
What is that?
for example, these that I said here will be relevant also for that, because yeah, I mean, finally, of course, in the detector you see the heavy light bound states. Most of the heavy quarks you see anyway as heavy light bound states, because you create them in a hard collision, and then of course typically the quark and QQ bar will go in opposite directions, and then of course only a very small fraction, like less than 10% of them actually bind to give a quarkonium. And then in the detector you will see them, but you will still say, well, if this particle was very energetic and it didn't interact enough with the medium, then it will have certain kind of energy profile in the end. Okay, so I can ask these questions about energy loss and how well they are thermalized, etc., depending on those heavy light. But this other argument that I gave, that they will not bind unless they bound initially, of course is not true for the heavy light mesons. I mean, eventually you will see the heavy light mesons, because where do the heavy quarks go otherwise? So, right.
But I was asking it just because of what you said, that the chances of forming a QQ bar bound state seem much smaller than just forming heavy light. So
Yeah, the chance of forming a heavy light bound state is of course 1, because eventually it has to form a bound state at the freeze out, right?
So that's
Right.
right. So if there are signatures there, then you might be
Yeah.
able to use them more efficiently in a sense.
Yeah. So use them, yeah, to study the thermalization. I'll say a little bit
As
about
he
that.
said, a single heavy quark always has to go into a heavy quark and a light state.
Correct.
So whether it went through plasma or not, you will never know.
Okay, but I was wondering if let's say it's surrounded by deconfined plasma
Yes.
and it goes through that and eventually of course forms a state. Maybe the I don't know.
No, what I'm saying
there a
is, no,
signature
imagine
there?
two states, one which is vacuum, another which is plasma, and just single heavy quark. When it goes through, eventually it has to become a D meson or a light heavy state. So it doesn't really know unless, as Saumen said, you go to the last point of his thing where
Yeah.
you study thermalization properties, which he will tell you.
Yeah. In fact, if for some reason the D meson stayed as D meson inside the plasma, there's no reason for it to be so. But if it did, then you would expect this thermalization to be much slower, because that's a color neutral object moving through a medium. It doesn't directly interact with the gluons except through dipole kind of interactions. So the interaction strength is smaller. Okay, and what we'll see is that at least for low energy or low momentum D mesons, you see that the thermalization pattern kind of follows what you would expect for a heavy quark moving through the medium and not a meson. Okay.
How big is the binding energy of these heavy quarks?
Yeah, right. So depends on how you define the binding energy, of course. So I guess so all of them have ground states which are heavier than 2 MQ, no matter how you define MQ. Okay. Because there's a linear part, right? Yeah. So the natural question will be, so the free state is not 2 quarks. Free state is, let's say for charm, the free state is DD bar. Okay. So then DD bar energy is 3700 and J psi is 3100, so something like 5 to 600 MeV.
And lambda QCD is how much? It's about?
About 250 MeV or so.
250.
Yeah, depends on how you define how many flavors, etc. For 3 flavors, it's more like 300, but yeah.
So just to be clear, if this binding energy was much larger than lambda QCD, then I would have expected that at temperatures of order lambda QCD, it would just stay bound.
That's right, yes. So okay. So
that
why
wasn't
was it
so clear to
interesting?
me. It
Yeah.
wasn't so clear to me in this dissolution.
Exactly. So that was Matsui and Zat's thermometer argument actually. So the argument was this. So let's say this is my heavy quark antiquark potential in a confined phase. So there's a 1/r and then there's a string tension. Okay. Of course, in the deconfined medium, you would expect it to be something like this, a device screened 1/r. Okay. And then depending on where the hadron was sitting in this spectrum, so if the hadron was sitting somewhere here, you would expect it to be bound. If the hadron was sitting here, you will not expect it to be bound.
And that's measured roughly by the binding energy.
Exactly. Yeah. So that's what the argument was, that J psi probably will dissolve almost at Tc, but epsilon, which is a larger bound state because it's heavier quarks, will survive till higher temperatures and stuff like that. So that was the argument. And the reason why experimentalists love these kinds of signatures is because these objects are very easy to see in experiments. The J psi and epsilon, they couple to the Drellian, the dilepton channel. Okay, J psi has almost a 5% probability of going to mu plus mu minus, 5% probability of going to E plus E minus. And this is the region where the dilepton background is kind of small because the energy is large. And then you see this beautiful, nice peak in here. And so deconfinement will mean that you don't see that peak goes down. Okay. Okay. So what did people see? Well, there was early data long back already in the sun space, which was these energies that I was talking about, 200 GeV per nucleon. In that scale, it will be like about 18 GeV per nucleon. And there what they saw was that for 18 GeV per nucleon stuff, so this is the ratio of what you would expect if there was no plasma formed to what they actually saw in the experiments. These are, and then this is plotted against number of participants. So essentially, the idea is that the two nuclei can collide like this, or they can collide like this. You are much more likely to form a plasma at a higher energy in this situation, okay? Because we have a more head-on collision, lots of particles, so a larger plasma. And what they saw is that in those cases, the ratio of the theory versus experiment was lower than 1. And this created quite a bit of excitement, and the paper that they wrote on this title was Evidence for Deconfinement of Quarks and Gluons. So they thought this shows deconfinement. Actually now we are not that sure, but okay.
So, the y-axis was number of these heavy.
Yeah, that's right. So no, y-axis, y-axis is yes.
Number
So how many particles you see? Yeah,
Okay.
divided by what you would have expected if there were no plasma. X-axis is this number of participants. So this is like how central the collision is. Okay, and you measure that by saying, well, the more central the collision is, the more total charged particles you will see. Okay, so from that you kind of back calculate to say what's the
size of the fireball.
size of the fireball. Yeah, given by how many final state particles you got, total number of particles. Yeah.
So basically, as you go further out, you think you're forming a bigger and bigger plasma, and this affects.
That's right, yes. Okay. Okay, and right, now let me show you the result from current results. So LHC and compared with the REAK results. So these are the REAK results, the blue and the green, and these are the LHC results. So again, plotted against number of participants, and there are two things.
Is the same ratio
Is the same ratio, yes. Okay, and there are two things that you note. I mean, it's not obvious from this plot, is that typically the suppression is less than what you would have expected if indeed you formed a plasma at 18 GeV per nucleon in a collision that I talked about before. And more importantly, the LHC results at these red points, they actually show a lower suppression than these objects. Okay, and this makes it kind of complicated. The only way you can understand this LHC suppression being less than these suppressions is that you are also having some final state J psi. Okay, I mean, the charm density is sufficiently large at these temperatures that you can actually form some.
LHC suppression seems to be absent rather than less.
No. Well, so the no suppression would be like 1. Okay, so you see something like 60%. Okay.
So the idea is that you just form more charm and anti-charm pairs.
Right.
Because of the high energy.
That's right. Yeah. And some of them actually, yeah. Some of them actually can combine, even though they will not have combined in the initial state, they might combine at hadronization or something like that.
I think one should perhaps also give the disclaimer that the red points and green or blue points are more apples and oranges compared to.
Yeah, well, yeah. No, so there are differences in the rapidity window and all that stuff.
Details written in the fine print.
Yeah.
On the red point, you will see that it is mostly in the forward region. The y is a variable which goes from -4 to +4 in that particular thing. At 0, it is central. And if you see the blue and the green, they are covering y which is symmetric around 0.
See, I thought this is already sacrilege to show experimental data with error bars in QST seminar. This is the first time this happened? And then to actually talk about rapidity and all would be.
Whenever the speaker wants to impress us, he shows error.
No, but experimental error bars. I'll also have some theory error bars. But
Just to complete that, so somehow the idea is covered, then that may be a different kind of test of.
Yeah. So essentially, people who try all kinds of feeds to feed the data finally conclude that you need some amount of regeneration to feed the data. So I told the conclusion. Okay. Then I mean, actually, you can play around a lot using these aperitif windows and this and that. Yeah. So.
And is this expectation that the heavier quark bound states are less suppressed? Is that borne out?
Heavier quark bound states are less suppressed? No, because the light quark bound states are coming from everywhere, right?
No, he's talking about epsilon.
Oh, they are less suppressed, yes.
That is borne out.
Yeah, not maybe in LHC. I'll next slide. Okay. Oh, I only have LHC results here. Sorry. So you don't see too much of suppression of epsilons in the
Epsilon
REAK.
is that symbol there is pronounced
Red.
epsilon?
Yes.
Okay.
Yeah. So these reds. Okay. Look at these red points, and then there are quite a bit of details. So quite a bit of epsilon 1s is the ground state epsilon. Okay, then there are excitations which have less binding energy, and in that thermometer argument you would expect them to decay more readily. Most of this decay of this, most of this suppression of the epsilon you can understand by just saying, see, all the epsilons that you see in the detector ground state epsilons do not come because of a primordial ground state epsilon. For example, higher excitation state epsilon can decay into ground state epsilon, or some other BB bar pairs like chi or something can decay into epsilon, and most of this suppression can be understood as coming from that. Okay. So
What was the argument again for this epsilon thing? Is that if you have higher binding energy, then you need more screening to unbind them.
that's right. So for example, you have infinite mass. Okay. Then the separation between the quarks is 0. Okay. They form a bound state just coming from the Coulomb part. Okay. And so a Bohr radius of 1 over alpha m goes to infinity, separation is 0, and then what does it care about a temperature of a few hundred MeV? Separation scale is much
more temperature to
exactly. So yeah, right.
Yeah, the screening has a length scale. And the length scale is just much bigger than
Right.
the size of the
Right.
so who cares?
Right. Okay. Okay. Now I already said some of this, but actually getting to these data points, as always with
Sorry, Saumen, I didn't quite catch what you said about if it's important. Just could you say it again? You said all of this separation could be understood by decays between things. I didn't.
no, I am not sure about all. So the CMS earlier results were completely consistent with. So you know what fraction of. So these are stuff they actually study by looking at epsilon and associated stuff and all that. They actually study how many epsilons are what they call generated as epsilons, and how many prompt is slightly different, I think. But direct epsilon.
But just an elementary point. Whatever process you're talking about, why don't they also happen in the vacuum? It sounds like
They happen in the vacuum. Yeah. So I'm taking the ratio. See, anything that is different from vacuum, I will call.
I think the simplest explanation is that the red points can be explained by the vacuum processes essentially.
Okay. So no.
Why aren't they at 1?
Yeah. That's the point. See, you are saying you have epsilon 2s. So that was this plot that I had drawn before. So let's say this is my heavy quark antiquark potential, and some bound states. If you now, so this is R, and some bound states, let's say, sit here.
Yeah.
And some bound states sit here. So epsilon 1s, let's say, sits here. Okay. So then if temperature is such that the screening length is less than this, then epsilon 1s you would expect to decay.
Yeah.
Okay. However, these objects will decay if, let's say, the screening length is somewhere here. Then these decay. Okay. And finally, of the epsilons that you see in the detector, quite a few are coming from, so let's say, an epsilon.
Those that would have started out as bigger.
That's right. Yeah.
Those are not there.
That's right.
I am.
So, yeah. Okay.
The ones which were bigger bound states,
Yeah.
which decayed to smaller ones.
Right.
They were never created, so they never decayed to the small ones.
So you have created in your collision a CC bar pair. Then there is some probability that this CC bar pair emits some gluon and goes to an epsilon 1s. some probability that it goes to epsilon 2s, 3s. In fact, I think the probability would be slightly higher that it goes to the excited states, because then you emit a lower energy gluon. Okay, let's say you are just above threshold and then you emit a low energy gluon, you go to epsilon 3s. You need to emit a slightly harder gluon to go to epsilon 1s. So actually the probability is slightly higher. Is that correct, Rishi? The probability is.
I don't remember it. This is low PT. So at high PT, I think 3s is less than
3s is less than
1s.
okay.
But at low PT, I don't
Yeah,
know.
okay. Anyway, but there is a finite probability that it goes into some of these other stuff. And you expect from various experiments where you actually try to track just as epsilon 1s is coming, so you get this mu plus mu minus coming from epsilon 1s, and you try to see if there is some other lepton pair that is coming from the same vertex and stuff like that. And from that you try to estimate how many of these epsilons are coming from decay of some other BB state, okay, in vacuum. And then let's say only 40% of epsilons are coming as directly generated epsilon 1s. Okay, 60% were coming because of dissolution of other excited states. Then you would say this plot is completely consistent with all the higher states going away. All the higher states, see, those states cannot form, therefore they cannot decay to epsilon 1s. Okay.
And is that the case?
So that's what I was saying. So I think then the line should have been somewhere here.
I see.
So the earlier data was completely consistent with that. In fact, this earlier data had a beautiful plot where they show that the ground state peak was, so they had a plot which looked like this. So this is the PP bar expectation, let's say, and then the heavy ion collision you see this, and then this, and then this. So the ground state is what you would expect, and this. But I think these numbers are slightly smaller, so you would, but then maybe there are errors, I don't know. At 2 sigma or something, they are consistent with just the ground state. Staying. Yeah.
Just a stupid question. And the notation you're using is hydrogen atom line. So is the effective model for these things effectively a hydrogen atom?
So you look at the, so typically you, so you take the L is equal to 0 states and the ground state of that you call 1s. Okay. And so on and so forth.
I was going to ask you, what about 2p?
They're there. So they are more, okay. So for them, the quantum number would be something like, so it will be something like Schreiber, psi, let's say, a scalar. Scalar is a L is equal to 1 state. Then I think an axial vector is an L is equal to 1 state, because they have, the parity gets changed. So the vector, if it is 1 parity, the L is equal to 1 state will have a minus 1 to the power L. So the parity would be opposite. So epsilon 1s is ground state. So the other one is axial vector. Okay. Now axial vector does not connect directly to mu plus mu minus channel because it doesn't go to a photon. So studying them is more difficult. Okay. Okay. So what I was trying to say in this slide was that going from going to that actual data is much more difficult, which I do not do. I mean, we are just interested in telling what happens if you have a simpler system. So given a temperature, you assume that you have a kind of equilibrated plasma, then what happens to these states? That's what much of the rest of my talk will be about. And then actually the plasma that you have is fast expanding and all that, and therefore you need to do some kind of hydrodynamic modeling of all that. And this is one of the inputs that you put in there. At a given temperature, what happens to the plasma, and then you fold it in your evolution model and stuff like that to get to that data. Okay, so how to calculate interaction of quarkonia with medium? So in a sense, this is the beginning of my talk. So
You have an article.
Right. So okay. So how to calculate interaction of quarkonia with medium? You take a meson and then let it decay. So for example, for J psi decaying to mu plus mu minus, you will have a vector current which will mediate that decay, and therefore, so this is the uninteresting leptonic part, mu plus mu minus part, And what you will get essentially when you take mod m square of, mod square of this matrix element, you will get a J mu correlator. Okay, and then you want to study that J mu correlator, and in particular, after all,
Really sorry. J mu is what? Which current?
this is the vector current. I've just I'm just
Which symmetry?
so C bar gamma mu C. So let's say a J psi is going to a mu plus mu minus, right? So I know what happens in the mu plus mu minus side. Let's say I'm trying to draw a diagram of this.
I'm really embarrassed myself. I don't know what J psi is. Can you just say that?
Oh, so I'm sorry. This is the vector. So vector ground state of C bar C quark. Okay, and then you know that mu plus mu minus will come from. So this is a vector. So I will have this coupled to a photon.
J psi is the one which got Nobel Prize for physics.
But before his birth. So right.
Yeah, but it has hybridized features also before you were born.
Hopefully I know before I die.
Right. Yeah. So right. So this illustration that I gave was for J. I mean, not illustration. That was real data. Oops. Where did it go? Yeah. So this was the J psi peak. So it beautifully couples to the mu plus mu minus channel, and this was when they saw this, they called it November revolution or something, because this was like so surprising, such a sharp peak at energy like 3 GeV. People didn't know of charm then. Okay, so they realized it has to be a new kind of current.
And that
And
photon that you're showing there is
Actually, photon.
it's really electromagnetic.
It's an electromagnetic photon. So how do you create a mu plus mu minus here?
So the current is the electromagnetic.
Current is the electromagnetic current, exactly. Right. So of course the mu will couple to a C bar gamma mu C current. The current that will mediate in this process, the vertex that will mediate in this process is the C bar gamma mu C vertex. Okay, and then what I'm writing there, so this is my J mu. Okay, and so the leptonic part, of course, you can write down the Feynman matrix element, and the hadronic part you just keep it as J mu that takes an hadron and makes into a vacuum. Okay, and then you do the
Hadron being your J psi.
hadron being my J psi. That's right. Okay, and then you take well, of course, for thermal systems you take hadron plus whatever else going to whatever else. You do the mod square of that. You take sum over these whatever else states, and then you get the thermal correlator, which is like e raised to minus beta h, J mu x, J mu 0, something like that.
And the U bar V, that's the final.
Those are for the electrons. Okay, right. And then with all those standard manipulations that you do with these kinds of correlators, you connect these to a Fourier transform of Fourier transform of the commutator of these currents, which is called the spectral function normally. The connection of this object to that is through a Bose distribution. Okay. This just comes by you put in a complete set of states in between and do a couple of lines manipulation and get this form. Okay, and then this 1 over the photon propagator gives a 1 over q squared, that becomes 1 over q to the power 4. There is alpha in this vertex, alpha in this vertex. Sorry, g in this vertex, g is in this vertex. JH is this C bar gamma mu C. I have changed notation. So J mu. Okay, yeah.
J mu that 0 J mu h, right? That's
So JH will be J mu for J psi. I wrote the general notation because if you want to study some other hadron, then you take some other current.
No, but where is the J psi? This expectation value is taken just in the thermal state, right?
That's right.
So in the first thing you had some J taken in an H.
That's right.
Has that information survived there? I mean, is that JH just C bar gamma mu psi, or is it something more complicated?
JH just C bar gamma mu psi, yes.
So the fact that it's the H information has gone away, that you were doing it in the J psi state has gone away?
That's right, yeah.
Why?
That's what I was saying. So what you do is you take the mod square of this, okay, take e to the power minus beta ai, and then sum over all the initial and final states. So this is a complete set.
Why is it? I thought you were looking at it for a particular hadron H. That's a complete set.
So that's like an outlier. So I'm not taking that as in the thermal states, right? So
I didn't understand. That H there was a particular J size state, right? Or not?
the H is a particular J size state. So okay. So okay. So what you are doing here is you start with so let me write this state as some whatever n, then j mu, and then h, the hadron and the n.
Yeah,
Right?
particular state.
Particular state, that's right. And then you take mod square of this okay, you are doing thermal.
Good. So you sum over all n with whatever weightage, but your Hn is fixed.
Right. So
There seems to be like a thermal state in which that hadron is always present. There's
no,
some
no. Well, okay. That hadron, well, okay. So that hadron is not part of your thermal bath. So that hadron is given from outside, and then you are so what is the difference between my initial state and the final state? In the final, in this state, I get a okay. So I take the j mu and then
Is there a square in the commutator?
sorry.
What Shiraz is saying is it should look like a 4-point function. A thermal 4-point function rather than a thermal 2-point function. If the commutator has a square,
No. There is no square.
then it's arrows from the center.
I think the states which don't have a H in them anyway will not give J mu acting on that will not give any contribution. So
You're saying J mu acting on vacuum gives only states which have an H. That the H's are a complete set for J mu acting on vacuum. Is that the claim? If so, then that's right.
Yeah, that's right. Yeah.
This is
So-
C bar C. You know,
This C bar C.
yeah.
Heavy light, for instance.
No, well, okay. So you could create two heavy light.
But also there are many, this is decay of a J psi, right? There
Right.
will be high excited states
Of the J.
of the CC bar system. They will surely couple.
That's yeah. No, that okay, yeah, that is definitely true. So what you will get in this expectation value is not only the JSI, but all states that all Sieber-C states. So you don't allow multi Sieber-C states. You allow single Sieber-C states. All Sieber-C states in the vector formation you allow that get created by this J mu from this.
So maybe then the point is that only such states.
Only such states are there.
So why not C bar light, C light?
Yeah, so I think that in fact a part of the spectral function at the tail will
That's
then
right.
have that contribution
So
also.
this is an approximation. Yeah.
No. So you are taking everything that gets created that contributes in this.
Okay.
So
But I
So-
think you're doing this for the question of decay of a particular hadron. But downstairs, you're looking at something that is losing the information of what hadron was going to decay. So it seems that these two cannot be equal.
that's okay. So that's correct. So only in the okay. So now if you restrict yourself to the region in energy momentum where it allows only a JSI creation, okay. So if Q is such that it allows only one JSI creation from the thermal state, then this will give you the JSI peak.
Approximately. It will always allow arbitrarily.
It will always allow arbitrarily. That's right. Yeah.
So there's some approximation.
Right. So what you are doing is okay. So I think maybe it's better to go from this state to this state.
Yeah.
So this state gives you the total dilepton generation cross section. Yeah. Okay. So yeah. Right. So let me say it like that. Yeah. So this correlator, what this is giving you is the total dilepton generation cross section at this Q. Okay. And then you expand it by putting in those H states, complete set of states.
Some
Okay.
of them are H's, some are not.
Some of them have H's, some of them do not have. Okay. And then,
function picks up which one is which.
yeah, exactly. That's right.
Or rather, at some values you're dominated by.
That's right.
The whole picks up.
So essentially, this will you would expect these to give that whole dilepton spectrum that I drew before. Okay. If this is in this Q regime, then you would expect this dilepton spectrum to be dominated by the JSI. And if you don't have that, if you don't see these peaks in this regime, then you say that you don't have the JSI
Different
anymore.
states are different poles, so you can zero in.
Different bounce rules. Exactly. Right.
And they are approximate poles because these things can decay.
Sure. Okay. So the point I was saying was that, the point I was trying to say was that this object is something that you can calculate non-perturbatively going beyond perturbation theory and all that. You don't make any assumption about the structure of JSI, its connection with C bar gamma mu C current. You just look at the C bar gamma mu C current. It's
Very clean observable.
yeah, it's a clean observable, right? And this is what I have said. So if this is dominated by a JSI pole, then you will see this. So in general, the structure of this object will be something like this. Okay, so there will be this sharp JSI pole and then other kind of structures, and then like you said, heavy light.
I'm curious about this notation sigma upper mu v comma lower mu. What does this mean?
Oh, that's just J mu, because you had a photon that give you a G mu nu. So you're doing what is good, yeah. Right. And now this spectral function can also be connected to the Euclidean correlator, which you can calculate from on the lattice. The hitch is that the connection is through something which goes like e raised to minus omega t. So it's not a very good observable to calculate, but at least in principle, so if you took
Sigma is what you're interested in, and G is that transform.
that's right. So you take this object and then essentially allow the momentum to go to. So you take, so you take the retarded correlator and then let the Q0 go to imaginary value, then you will get the Euclidean correlator, which you can calculate on lattice. But of course, then you are taking e raised to I Q0t and making it into e raised to minus Q0t. Okay, so So that's numerically kind of unstable. But anyway, so let me not go into how we try to study that beyond saying that it's kind of a dicey problem numerically.
So you compute the Euclidean quantity and then there's some techniques to continue it back.
Right. Well, essentially the technique is essentially to say that so normally in something like this, you would like to say, well, I know this object, then I do some kind of a fit to get into the sigma, right? But that doesn't quite work. And essentially the technique that we followed here was to essentially supplement this thing with whatever stuff we know about sigma as part of your analysis program in some way that I didn't want to get into. I mean, if you're interested, I have some extra slides, but essentially the kind of information that we are giving here is we can do perturbation theory at large omega. So we can give the form of this sigma at large omega to supplement, because here of course all omega modes contribute and all that. And then you hope that you get the omega region of interest to you correctly.
So I have a question about just the analytic structure.
Yeah.
So suppose we took this correlator in Euclidean space.
That's right.
Think of it as a function of time.
That's right.
Then as if the two spatial points and the two times become equal, there's a singularity in the correlator. And clearly, usually.
That's right, yeah.
Okay, now I'm analytically continuing.
Yeah.
So at least at times that are small compared to the circle size,
Right.
you would expect that singularity to continue along the light sheet.
Right.
I was wondering what happens to the position of that singularity.
Yeah.
Does it always continue along the light sheet, or does it curve? Or firstly, is it true that at finite temperature you have a singular?
So you were saying that at tau is equal to 0, this analytical continuation will not work.
No, no. I think the analytic continuation is fine, but the analytic continuation will have singularities, and you will have to know how to do which order to, how to go through the branch curves.
That's right. So okay. So yeah, it's not here, right? I was looking at it there. Yeah. Okay. So the idea is this. So let me give you the results on which we base the analytic continuation. So as you know, by default, this sigma, if you put this q Euclidean to q0 plus I epsilon, then you are expected to go to the retarded correlator. Okay, and this works for any tau greater than 0. Okay, if this object has at most power law growth with omega. Okay, so this is the result. The proof of this, that the analytic continuation work is kind of complicated. It's a lot of, I can give you the reference.
Right. Yeah. I just wanted to get a rough sense of the singularity structure. Suppose I work in position space.
Can I ask you just a prior question? Can you go back to the previous slide? So sigma has both dependence on omega and p, right?
Yeah.
And when you go to the next slide, presumably the p dependence just carries
I had
through,
just, the p dependence would carry through. Yeah. The studies that we have done are all for p equal to 0. So, okay.
Go ahead, please,
Yeah. So just to understand these correlation functions,
Yeah.
the analytic structure, and on the function of the T complex.
That's right.
Is it true that there are these non-analyticities that extend in lines on the complex plane? And next question is, does this line remain 45 degrees, or is it something different?
At finite temperature.
Certainly at small sizes it must, because that's your zero temperature.
In the T plane.
Yeah. So any singularity that happens at zero proper distance, in Euclidean space, at zero distance, continues to a singularity in Lorentzian space where at zero temperature that happens at zero proper distance.
Exactly.
Which
Right.
means along the line.
Right.
Now, because of the circle, you're breaking Lorentz invariance, so the statement is no longer 100% accurate.
Right.
I just wanted to understand what it is.
So couldn't it happen inside the light cone if the effective speed of propagation becomes smaller?
Yeah. For instance, at long distances, you might expect it to happen at c by square root 3.
Yeah, exactly.
That's roughly, yeah.
At long distances you can, okay.
Sandeep suggesting it happens not at the speed of light, but at the speed of sound, right?
Or whatever, yeah, exactly.
But it might, but you know, something about analytic structure is an exact property of a Green's function.
Right.
Might continue, I'm not so sure, yeah.
Right, right.
I mean, are there clear results about this just in the formal theory of finite temperature physics? Like the analytic structure of zero temperature Green's functions is well unknown from the 1960s.
Yes, yes. So this is the exact result that I was quoting. So okay, so
Just
I'm not.
repeat what was the exact result that at
Right.
tau different from zero?
So at any tau, okay. So first is that I have projected it to. So I have projected it to. So what I'm looking here is G tau p kind of stuff. In particular, I have taken tau p equal to 0. Okay. So the position information is gone, and what you can show looking at the analytical structure. So in the complex plane, of course, the sigma essentially picks up the singularity structure around the real axis. So the sigma is the discontinuity of the retarded Green's function around the real axis, right? So that's why you pick up the q0 plus I epsilon kind of stuff. Okay, so sigma is, I think, imaginary part of the retarded correlator as you put q goes to q0 plus I epsilon. So essentially you pick up the singularity around, pick up the discontinuity around the real axis. Because of the commutator. Well, okay, I mean, I can go through these results if you wish, but so showing this is not very difficult. What you can do is.
But does it come from knowing what the singularity structure was in position space?
Does it come from knowing what the singularity structure was in position space?
I mean, does it use causality for this?
I think this is causality, but
Which part is causality?
You may use somewhere that within the future light cone, the Green's function is analytic. Are you using it?
Yeah, I'm using that. Yeah, that's right. Yeah, right.
Okay, so you're using that the singularity, whatever it is, doesn't extend to outside the light cone, but you don't care how if it bends inside.
Yeah, right. Yeah. Okay. So the exact determination of this result that I quoted, that for tau is equal to tau greater than 0, this continuation works, is kind of complicated because of exactly this.
But I'll just ask one more. Is there a systematic analysis of this analytic structure of correlation functions at time?
That's right. Yeah.
There is.
There is.
Where can I find it?
Yeah. So I remember the first author's name. So there's a very complicated paper. It will be great if you read it because I have had difficulties reading it. Okay. Kuniberti, and then I think two others. Journal of Mathematical Physics. I think around 2001 or something.
Okay. I'll ask you for that.
Yeah, I can send you the exact reference.
Saumen, can you repeat the name?
Kuniberti, Cuniberti. I can send you the.
Okay.
I can send you the reference. Yeah. But the result I'm using here from that is that if this does not have more than a power law growth, then this analytical continuation works for tau greater than 0. Okay. Right. Okay. Let me skip this and go to show you some results about bottomonia from such analysis. Right. So what we have done here is, like I said, use that connecting equation between Euclidean correlator and the spectral function, and then given the large omega behavior, like I said, I give some information to it and I tell it that the large omega behavior is kind of perturbative, and then you get this kind of a peak structure for Bottomania, what you find is that so this green line is at 1.5 Tc, the blue line is at 2.25 Tc. You see pretty sharp peaks at the Bottomania energy regime up to something like above 2 Tc. Okay. The study becomes more and more complicated as you increase the temperature, so we stopped at 2.25 Tc, and you don't see dramatic change on crossing. First, you don't see any dramatic change as you cross Tc, so there's green and red, they are almost completely identical, and this is what Shiraz was saying, that the upsilon steps might just survive. Okay, and yeah, and then this pattern continues till above 2 Tc. Okay, we tried extracting what I can say about the width of these states. This is kind of this is ongoing. So the problem is that from these correlators themselves, the point-point correlator that I showed and that had all these theoretical structure so far, that was all valid for the point-point correlator. From that, it's very difficult to extract a width. Okay, so what I do is some kind of an hand waving where I take something like a smeared correlator. So I do not take a point correlator, I take some object which has some S wave kind of width, okay, in order to kind of increase the overlap with upsilon, and then I change the radius, hoping that if some properties do not change as I change the radius of the smearing that I have used, then that's coming not because of the smearing.
Sorry, is the smearing in your gene?
That's right, yeah. So all the properties that I have told you so far, which are nice and all, are for the point-point currents, Siva gamma mu c. And now I am kind of going outside it, but then I am hoping that an extrapolation in R0, so to say, works, and so things that are R0 is the smearing radius, so R0 equal to 0 is your point-point current, and then stuff that are invariant as you change R0 by a substantial value, they are probably coming from real physics and not from the singularity that you take. So that's kind of questionable, but the point is that you cannot use, especially if you want to do phenomenology, what they want from us is some kind of a width that changes with temperature. You cannot work with this one spectral function at 1.5 Tc, another spectral function at 2.25 Tc. They want something which is continuous and changes with temperature. And so the attempt was to see whether we can say something about its decay width at these temperatures. And in particular, I had focused here at 1.5 Tc. And okay, yeah, I'll come to the, so even after doing all of this, I could reliably only give some kind of an upper limit on the width of the upsilon. So first note that this width that you see in the spectral function, this has nothing to do with the width that I am seeing. Okay, because finally you are taking a finite number of data points and doing some analysis, it will always give you a continuous function and not a delta function peak, right? So the way the attempt to obtain the width is done is you fold in a Bright-Wigner kind of peak, okay, in that function. So far these were direct inversions that I showed you. Even these are direct inversions. And then you fold in a Bright-Wigner function and try to see what kind of width of this Bright-Wigner is disallowed by the data. Okay, so as you saw, there was very little change in the spectral function, and in fact this is a direct show of, if I take the spectral function below Tc and try to say that this is what is giving me the correlator at finite temperature, so there is no change in the spectral function, then how much is the actual data different from the correlator that you get that way? And you can see that they are very close to 1. So any large width will contradict the data. Okay, and when you look at this smeared correlator, then you get something like the width does not exceed something like 200 MeV. I will show it in a later plot. We should have had that value here. So just for comparison, the upsilon width at 0 temperature is like 50 keV. Okay. So you are in principle not disallowing a huge increase in width. Okay. So let me just, so this was all done with the full relativistic action, but very fine lattices you need because Bottomania mass is very heavy and your lattice spacing has to be much smaller than that. But you can also do NRQCD. Okay, you can do NRQCD on lattice, and this is what was done by these two groups, one in UK and one in one that is multinational. And they also saw that the epsilon and eta B ground states survive till pretty large temperatures.
Sorry, so you have this action in the NRK, non-relativistic case, and then you have the bound state of this action. Is it, or what is the?
No, so
Is
you
it a separate field?
no. So you look at the same kind of spectral function for the current. So these are the quark and anti-quark states now. You know the NRQCD action, right? I mean, okay, I have written the simplest up to 1/m kind of thing. They actually use a much longer expansion. And then because of this I del 0 here, I think so now you try to calculate I try to calculate exactly the current correlation function that we are doing in terms of this theta and phi, okay? And then it becomes kind of an initial value problem, okay, because of this I del 0, and then you try to calculate the correlator, then you try exactly the same analysis that I talked about. So all the uncertainties of that analysis go in, and that shows in the result. The two groups both using NRQCD get results which are quite different, okay. So they have kind of smooth peaks in one of the study, and they actually try to measure the width, both of them. They get pretty large width, they get extremely small width. The width again is attempted by, like I said, folding in a Bright-Wigner, okay.
So
And
at least at the claim level, is it a factor of 10 or 100?
I am showing you the, so these are the two NRQCD studies. One talks about a width which is like 400 MeV at 1.5 Tc. Now this is huge because you are not having a thermally equilibrated system. So a large decay width means the Bottomania doesn't quite get time to regenerate or anything. So most of the Bottomania will go away if the width is something like 400 MeV, okay, because you need to survive for quite a bit of time. On the other hand, the other study, they also gave an upper limit like mine. This is an upper limit, but mine upper limit was like 180 MeV, and their upper limit is like 10 MeV or something at 1.5.
You showed your own.
That's right. So I use these mirrored currents and then try to see what kind of Bright-Wigner width is disallowed by the data, and that comes to something like 180.
And use the full relativistic action.
The full relativistic action.
And less is
Yes, yes. It's consistent with 0. So mine is not inconsistent with this. It's inconsistent with
when
that.
you say quench, the light quarks are quenched? What is quench?
Yes. Okay. How long do I go on?
When lunchtime, so maybe 1:30 is.
1:30. Okay. So let me.
So just to understand, these two different studies, they got very different results because they used what was different between them?
Well, the major difference, I think the major difference is in analysis, and even though my result agrees with, okay, so this, so it's like doing an inverse Laplace transform, right? So the analysis becomes kind of very crucial.
This is the analytic, no.
Yeah, this is this, yes, that equation that I wrote, okay? So if you have, so if I had some cosh hyperbolic, etc., that was just coming from periodicity in beta. Essentially, it's like e raised to minus omega t transform.
So both groups will get essentially the same results for the Euclidean correlator, and then the difference is in the continuation. Is this right?
That is right. I mean, there are subtler differences. I mean, so I think they have a final lattice. They have a final lattice spacing, I think, than them, etc. But the essential difference is in the analysis.
In the analytic continuation.
In the analytic continuation. And I think I am, this method is similar to our method, and at least in principle, it's a stable method.
Which one?
The one that with which my results disagree. I said in principle stable because,
LHC
Both of these are NRQCD.
Both of them are NRQCD.
Yeah. And the one that is getting narrow width is using some analysis that I am suspicious about, but okay.
But the red guy arcs,
Yeah.
do they require an upper bound or they say that?
No, no, no. So they have error bars. Okay. So these error bars, they mention that these are only statistical error bars. In principle, they will not totally rule out that there's a large systematic error and all that, but this is what they show in their paper. Okay.
Okay, so just to understand, all the calculations which don't put a bound but compute a number for gamma are NRQCD calculations?
This is also a bound. So,
Oh, that's also a
yeah,
bound?
yeah.
Okay. So, but every point here except for yours in pink are NRQCD.
That's right. Yes. So 2 NRQCDs. In fact, those results are mine. Like I said, is I didn't show you the CHARM data, which is old and published data. This bottom thing is ongoing, but essentially the aim was, so these are 2013, 2015. There is a big difference. So you try to see the relativistic action, what you get, and
They use relativistic action for the light quarks. Is this right?
yes. Right. So NRQCD of course has its issues. You cannot take a continuum limit because the momenta, you are allowing momenta of scale 1 over a, and that always has to be less than the mass of the bottom quark. So that was the motivation for doing relativistic action from my side. It's a different method.
That's what I was trying to ask. Whether
Yeah.
it's okay.
Yeah.
So, but the only relativistic calculation is yours.
That's right. Yeah. Okay. So let me. So there are also attempts to actually see whether you can actually give a potential. I don't know whether. Okay. Let me hop a bit here, and
This is for B bar.
this is for BB bar.
And that is the thing you were calling.
Oops. Yeah. So ideally, it's okay. Yeah, that's right. So I'm calculating the spectral function for B bar gamma mu B, B bar gamma mu B. That's right. And
And there's
the
data.
upsilon part is only that peak that you see around upsilon mass.
But there's data for this now, right?
There's data, yeah.
So can we compare these predictions with the data?
Sorry?
Can we compare the 3 different predictions with the data?
Not at finite temperature.
Oh, there's no. I see.
Oh, you mean experimental data?
Yeah.
Yeah. So that's what I was saying. So going from these two experiments is quite a few steps. And what the guys who are actually fitting to data want from us is something like width as a function of temperature. Okay, you give them these 3 spectral functions, they say, well, give me something that I can put in my hydrocode. I mean, for obvious reasons. So it's quite convoluted going from that to that data. Right. So you can, of course, try to also go to construct a potential for heavy quarks, essentially going to the NRQCD limit and replacing this in this q bar gamma mu q, q bar gamma mu q correlator, the q correlators by just a Wilson line.
Is N Tesla Max Dressler? No, that's Tesla someone.
Teslas?
Is that
Strassler. You mean?
Two letters missing.
Yeah. No. Yeah. So, right. So you essentially try to see if you start with this correlator, calculate it in the non-relativistic limit, and then take the large time limit, what kind of potential you get. And the answer is, well, depends on how you do the calculation. So for example, if you try to do perturbation theory, then you know that there are all these scales, and exactly how you do the calculation matters. You can only really do perturbation theory well if you take if you integrate out the temperature scale, so because you then go to the hard thermal loop calculation and all that. So you have to assume that the temperature scale is larger than inverse of the distance that you are interested in. If you do that, you get a potential which is like this. I mean, it's looks complicated, but it's just the Fourier transform of the hard thermal loop photon propagator 0th component. Okay. So there is an imaginary part, and of course we know what the hard thermal loop, imaginary parts of hard thermal loop correlators give, they essentially give the probability that in the thermal medium, because of scattering with thermal particles, thing can decay. Okay, and so
Saumen,
yeah.
just a question.
Yeah.
So I'm not able to understand this completely, but the point is that there's a finite temperature dependence to this width of epsilon.
Right.
Is it understood what is the leading correction? I mean, leading finite temperature dependent contribution to this width?
Leading.
What's the physics?
What's the physics? Yeah.
What's the physics that gives you leading temperature dependent contribution to the width of epsilon?
Yeah, right. So the physics, of course, would be scattering with thermal gluons. A thermal gluon comes and hits the epsilon and breaks it up.
Okay.
Okay.
So the particular expression that you're writing down is what I would get if I replace some kind of gluon with a thermal propagator for the gluon.
Exactly. So I think I have this.
Okay.
I'm going the other way. Right. So so this is the 0/0th component of the hard thermal loop thermal photon. So this is your, so this is at P0 is equal to 0. So exactly the object whose, so you know all these standard stuff about ladder approximation and all that, and then eventually you get the potential just by taking the Fourier transform of the P0 is equal to 0.
But is it, sorry, so this, is this understood? As in, like, does everybody accept that this is the physics, and we are just trying to,
it does.
The leading effect is due to the thermal gluons?
See that it has to be the effect of thermal gluons is pretty obvious, right? What else can it be really? Okay. Let me. I think I will say a couple of things about that.
Okay. So another question.
Yeah.
So this NRPCD research that you presented. So eventually everybody is just trying to calculate. I mean, I can say from a statement point, everybody says just trying to calculate what do thermal gluons do to the width of epsilon. You know, is that?
Everybody's okay. So let me go step by step. So in perturbation theory, what the width is coming from is very clear, because like I said, the imaginary part of the potential is what will contribute to the width, and the imaginary part of the potential is coming from, oh, I'm going the other way, sorry. This part of the hard thermal loop gluon propagator, hard thermal loop photon propagator, and then you know, of course, how to interpret the imaginary part in the hard thermal loop propagator, okay, in perturbation theory, okay. And that is exactly what I said, I mean scattering with thermal particles. Okay.
And here MD is the Debye mass?
Debye mass, that's right, yes, yes.
Okay.
Right. Yeah, so this was kind of an illustration of that, the imaginary part comes from this self energy, and then there's a cart, and that of course corresponds to mod square of a thermal process like this. So that was essential.
Sorry, if Loga is done, then I have a question.
Then in NRQCD, of course, what you are trying to do is you are just calculating the J-mu propagator. You don't care too much about what is the dominant process in that width. You are just trying to ask if there is a width. Okay. But
whatever temperature dependence you should get should look like it is correcting it is due to thermal gluons, right? Or
essentially, yes. Yeah. Right.
But do they look
So for example, you can so there's from NRQCD you can essentially try to focus on the bound state. So you can go to something called the PNRQCD Lagrangian. Essentially there you try to integrate out also gluons of energy scale mv. Okay. The idea is that the bound state energy is like mv square, and so you integrate out everything that is of scale mv. Okay. When you do that, then you essentially is Loga cut off now?
No, I'm here.
Yeah. If you do that, then you essentially focus on, so the NRQCD Lagrangian is typically written in terms of, so Q states rather than the PNR QCD Lagrangian, because you are essentially saying that the separation between the Q and Q bar, that's a large scale, and I integrate out gluons which have energy of the order of this 1 over R, okay, because the binding energy is much less than this, okay. And so of course when you integrate out gluons of this energy scale and then you want to talk about that length scale, then you will get a potential, things will get non-local in potential space, and that's what gives you this Lagrangian with all these potentials put in, okay. So singlet potential, so S bar and O bar, S and O here correspond to the quark antiquark in a singlet configuration, quark antiquark in an octet configuration, and the two corresponding potentials. So you will get, if you are calculating all of this, doing the matching in perturbation theory, then you will get that 4/3 alpha over R here and whatever is the octet potential for the octet case, okay. And then there are these terms which essentially connect the singlet to the octet through a color electric operator, okay. So this is the leading order m to the 0 term in here, and then of course there are other corrections, okay, which I have not written down. And in this kind of way of writing, then the decay of the singlet state will happen because of interaction with this color electric field, which takes it to an octet state, okay. So anyway, so you can.
Sorry, can I ask?
Yeah.
Just you're working at some temperatures, right?
Right.
Here.
Yeah.
And I didn't understand at those. If I look at the 0 temperature bound state of for the epsilon.
Yeah.
What is the size compared to the temperature?
Yeah. So actually, this perturbation theory shouldn't.
Good or not?
No, it's not good.
It's not good.
So typically, if you are trying to ask, so let's say I take the standard Cornell potential, which fits the Bottomanian spectrum pretty well, and try to ask what is the separation between Q and Q bar in an epsilon, that will be less than 0.2 Fermi. So 0.2 Fermi. So inverse of that is 1 GeV. And the initial temperatures that I quoted here are like 450 MeV. And then of course it evolves in temperature to go to lower temperature. So it's not valid. But in principle, so yeah.
But why do you say it's twice? It's not too bad, right?
But I did the other assumption, right? I assumed that temperature is larger than 1 over R to come to the hard thermal loop Lagrangian. Yeah. Right. So you cannot first integrate out the temperature. In fact, what really happens here, if you look at MD, the lattice estimates of MD, so even T greater than GT. So I say GT, but actually what I mean is T greater than MD, right? This is not valid either. Okay, so right. So that's why, at least in these temperatures, of course, eventually it should be valid at very large temperatures, but not at the temperatures that we are interested in. Okay, so that's why it's not a surprise that perturbation theory doesn't work. Otherwise, of course, things would have been much better. We took that potential and we calculate the width. But anyway, so you can now come from this picture. 5 minutes. I'll skip basically the next part, and essentially what I'm trying to say is that, so in this PNR QCD Lagrangian.
Don't skip your punchlines.
No, I'll show the. There is one advertisement slide, so of course I have to. Right. So in this, like I said, because this is good because this kind of directly talks about the bound state, and like I said, essentially here in this language, the singlet width will be connected to singlet to octet transition going through interaction with the color electric. So basically from this term. And then if you want to calculate the imaginary part of that thing, you will essentially get to a electric field correlator, right? Now this electric field correlator, okay, so there are certain outside factors, you do some approximation to them. So you start from this Lagrangian, and again in these references they have calculated that you can go back to the potential that I showed before. If you do in perturbation theory, you come to HTL, you do the integrating out scales like that. But of course that's not the scale we are interested in. If for example we take that inverse of R is much larger than temperature, which is true for Bottomania, for Charmonia it's not, but anyway. And then let's say I say that from this thermal correlation function I can take the R completely out. Okay, I'm just trying to get something which I can calculate on lattice right now. Okay, and then I say nothing changes about this R. I don't put it in thermal correlator. I just replace it with the bottomonium radius, R square for bottomonium state at ground state. Okay, then this converts to an electric field correlator, which of course again by similar analytic continuation and all I can calculate on lattice. Okay, so this is kind of I mean at a very, so I have not really examined the errors I am getting into while I do this, but the point is that this electric field calculator was actually already calculated by us to get to a diffusion. So you take a heavy quark in the medium, and then because the heavy quark is so heavy and its typical momentum is much larger than the temperature, than the gluon energies, therefore its energy doesn't change much, and momentum doesn't change much in a single scattering and all that. Therefore you can kind of give some kind of a Lajoie description for its motion. This was discussed quite long back, and then you can try to do your bit in calculate in this description, because once again the Lajoie description is fine, but when you try to calculate this coefficient for the force term from perturbation theory, you get dramatically wrong results. Okay, this was actually first put in a language where you can nicely calculate this thing in lattice, so kind of an electric field correlator in an ADS-CFT paper, or at least the first reference I am aware of. So these guys put it in this language and then calculated it using ADS-CFT. Okay, and actually the value they get is pretty close to what you get from lattice, but okay. Well, so then you use so kappa is what is directly coming from these force correlator, and then you normally you represent it using Einstein relation in terms of diffusion constant. Okay, but what you calculate is actually this kappa. Okay, and then d becomes 2t square by k using Einstein relation. Okay, so the other interesting thing they found was that for ADS-CFT, this correlation function was pretty smooth. This is just proportional to omega. So what we tried to do is try to calculate this correlation function on the lattice, and from that extract the kappa, and it was actually just published in 2012. But what I am showing here is an update of that result in 2015. It's in conferences, and then we span this temperature range, and there's another value at a single temperature, but more high statistics, more controlled study. So another
what is on the y-axis? Kappa? What is kappa?
Yeah, so kappa is this stuff that is coming from this force correlator. Okay,
It's related to 2-point electric.
it's related to that side. So it's essentially this force term in the evolution of in the momentum loss of the heavy quark. Okay, and then because it's a heavy quark, it's the force is coming from the color electric field. Okay, right. And this is the advertisement part. This is a slide from Vedanga's last year's colloquium.
I know it's late and you can tell me later, but is this picture the kind of opposite one in that here you take the bound state, let's say, to be much bigger in size compared to the temperature. Then you just think of color lines and you think of how they diffuse.
Exactly. So this is not for bound states. That's right.
Okay. Good,
Yeah.
Good.
So this is for single. So essentially the object that we calculate is something like a Wilson line going with two electric fields put in somewhere there. So this is the evolution of the static quark, and then these are the color fields in between.
I mean, it seems like these are the only two limits in which you can do anything except analytic. One where the size is much smaller than, you know.
Yeah, right. Yeah, yeah.
The other where it's much bigger.
Yeah, right, right. Yeah, right. But these, of course, you can directly study. So this is not a kind of an This is not something that you do only because you want to make some approximation to that width. That was, like I said, just a kind of a recent thought, and I have not really examined the errors in that. But but what I wanted to show you was that this actually seems to fit the data quite well.
Examine this diffusion, you send in not a QQ bar pair. But
So what they do in experiments or in phenomenology is that they actually look at the flow of these particles, see how much the heavy light quarks flow, and then they need to know the momentum distribution of these heavy light quarks. Okay, you start with a momentum distribution which you get from PP collisions, and then you see how much the momentum distribution changes, and in that all this diffusion description comes in. So you do some kind of a Fokker-Planck equation, blah blah. Okay, but this kappa is your input in that. Okay.
again, we can talk later, but the lattice fits well with Rick, or what is the?
Yeah. So that was the advertisement actually. So this was the slide from Vedanga's colloquium last year, and in fact I remember this slide. I asked him, "Can you please send me that slide for this talk?" So right. So this is what star says the value of D should be, and if you take our kappa and then do 2t square by kappa, these black points are from this is from the 2012 result. What I showed you is kind of update, but it's in agreement with this. Yeah. Now if I take this whatever relation kind of strong-headedly and try to see what kind of width that predicts. So I take the electric field correlator from that whole study, and then try to plug that in that width formula that I showed before coming from PNR QCD. Then I get this green band. Okay. So these are the kind of plots that experimentalists would love, but I think one needs to, because you can straight away use this in that thing. But like I said, I mean, I've not really thought about all the mistakes that I'm making here. Okay. Okay. So sorry about going a bit over time. I think we don't summarize. We heard the results.
Loga, questions?
No, I don't have any further questions. Thanks.
Okay. Kulaba.
I'll ask you one question which every student here will beat me up for, but answer me later, which is, when quarkonia decays was studied way back, also there was a color octet story, etc., etc. And
Do you mean decay or production?
No, that was in production.
Yeah.
Production.
Ask him. See, the point is, we
you're using a
yeah. So this is the singlet to octet transition for the decay.
I understand.
Yeah.
But I was just
And there it's the other way. See, basically in very high energy collisions, how will a quarkonium come? How will a CC bar KR come? I mean, eventually you will have some gluon which splits into a CC bar. But of course, if there is a gluon that's splitting into a CC bar, you would expect that to be a color octet. And the transition of that to the quarkonia, etc. So you have various stuff, and which of course survive till the next set of data come. And finally, of course, Anurag and Rishi are going to give us the answer that is going to live forever. But that's what he's working on, Anurag.
because this is kind of related in a way.
Yeah, actually Rishi had, even within this context, I mean, you had talked about this singlet to octet transition for decay, no? I mean, but I...
So there are processes where you convert, so for example, if you produce something in a color octet, it propagates differently through the medium compared to a singlet because you can emit gluons, and that gives a modification to the phenomenology of.
Right.
Even the production.
Yeah, the production makes an effect on it.
But didn't you also have a singlet to octet transition through collision with gluons in your study? No.
No.
Okay.
other questions? Okay, let's thank Saumen again. Saumen's not free for dinner, so there's no